It's been a great week at Splash, at the Plateau Workshop, at the Splash Education Workshop on Monday, and just at the main conference itself. I've really learned so many valuable, diverse perspectives on programming language research. And that's actually what I want to talk about today, is perspectives, and how these perspectives shape the research that we do. In particular, I want to talk about the perspectives on programming languages that we don't usually consider in computer science, and try to convince you that there are more perspectives we should consider than we actually do. I'm going to do this by starting on a somber note. We lost a great researcher, a great scholar, a great man, Seymour Papert, 3 months ago. He did many incredible things for computing, including computers as thinking tools, thinking about theories of learning like constructionism, the beginnings of neural networks with Marvin Minsky, and it was really an instrumental part of the One Laptop per Child program. But it wasn't just these discoveries. He also had really big impacts on a generation of impactful researchers. Alan Kay of Smalltalk, the Dynabook, object-oriented programming and GUIs. Terry Winograd, who helped found Google and the D School at Stanford. And Mitch Resnick, who started Lego Mindstorms and Scratch. We have to step back and ask, where did all of this incredible impact come from? Where were these ideas coming from? Papert actually wrote about these in the early 90s in his discussion of epistemological pluralism with Sherry Turkle. And his claim was essentially as follows. It was, the formal mathematical view of computing is powerful, but it's really not sufficient. It's not sufficient in particular for this goal. Papert said, equal access to even the most basic elements of computation requires an epistemological pluralism, accepting the validity of multiple ways of knowing and thinking. So the bottom line here was that if we want to involve the world in computing, and really involve everybody in the world in computing, we have to accept the multiple ways of knowing and thinking about computing that people engage with, beyond the perspectives that we use. So the question that I want to ask in this talk is, what are these other views? One view is that computing essentially is math. Another view is that computing is a thinking tool. This was Papert's view. Most of us in this room take this formal view of computing. Papert took this other view and found it highly productive. What are all of these other ways? I'm not going to take on all of computing in this talk. I'm going to just specifically focus on programming languages, like a slightly smaller focus. And I want to focus on a couple of claims. One, there are multiple ways to view programming languages beyond these two. And two, these views have a vast potential for discovery. This is something that we should discover. That's going to be my argument. And this is going to be my approach. I want to mine my own experiences for different views of programming languages over my lifetime. So it's actually going to be a fairly personal talk. And I want to explore these views as research agendas and try to understand what capacity they have for discovery that we might pursue as a community. So let me go ahead and jump right in. I'm going to start when I was at the age of about 10 in middle school. I want to talk about the first program I ever encountered. I encountered it in this building. This is Athey Creek Middle School. I was a 7th grade student. I was about 12 years old. I was in a pre-algebra class. And at the time, I was really in love with games, particularly my Nintendo Game Boy. Now, our teacher had required us to buy a Texas Instruments 82 graphing calculator, a TI-82, and he showed us a little bit about how to program it. He showed us how to enter trigonometric functions that we could copy from a piece of paper that he gave us, to shortcuts to computing various things about trigonometry that we were learning. That was, of course, not at all interesting to me or anybody else in the class, but I had a classmate with an older brother who knew all about how to program the thing. And he showed us this version of Tetris, TI Tetris it was called, and it rendered it on the graph. Tetris was one of my favorite games of the time, and so I had to get this game. We didn't have the internet at the time, we couldn't transfer the program, so I cut out the card in the mail order part at the end of the instruction manual so I could transfer the program to my device. And a month later I got the cable and the program, and this game, it was just this beautiful functional replica of the Game Boy version that I adored, with one caveat. It was just unbearably slow. You could watch the pieces erase pixel by pixel. So I was so disappointed that I couldn't play the game in class. I realized that it was a program like the one my teacher had shown us, and so I pressed the F5 edit button and was suddenly faced with tens of thousands of lines of conditionals and go-tos and variables, all written in this language of TI Basic. This was the first computer program I'd ever seen. And rather than viewing it as sort of gibberish that I couldn't comprehend, in this particular context, it was something very different. It was a form of power that, if I acquired, would allow me to bring my favorite game to school in disguise to play with my friends. And so I sort of ventured on this journey. I got the instruction manual. I read it back to back. I learned the language of TI Basic so I could understand how it expressed these rules in the game. And about a month later, I'd removed all of the rules that slowly rendered on the plot and instead rendered vertically on the text console, which was much faster. So you could flip the calculator around and play it in that vertical column. And I had a playable version of Tetris on my calculator. I took that link cable, I shared it with everybody in my class. It got me fame and respect and glory and actually a little bit of detention because the teacher suddenly had his whole class playing Tetris instead of doing trigonometry. He actually had to outlaw the graphing calculators from our class for that reason. Now, TI Basic was not a programming language as we conceive of it. It was a way for me to exert control over the game, to tell it to behave differently. But it was also a way for me to exert control over my classroom. I got to shift all of my peers' attention to this game that I loved instead of algebra. And so throughout middle school, programming languages for me was a form of power over my class, my peers, my teachers, my experiences at school. It's a really different conception of what a programming language is. And this has a lot of implications. One, if programming languages are power, and with great power comes great responsibility, what responsibilities does knowing a programming language entail? For example, why aren't software developers in the United States responsible for the failures that they cause? This is a powerful ability. What should we do with it? And if power corrupts, how does programming languages corrupt people? Take, for example, Mark Zuckerberg. He amassed a great power by knowing and harnessing programming languages to express social experiences. But he actually took that same power that he'd amassed through all of that money and tried to reform Newark, New Jersey public schools. And it was widely considered to have failed miserably because he believed, he understood sort of schools and education so well from this power he'd derived from programming languages that people perceived him as wasting hundreds of millions of dollars by really not listening to experts. So perhaps programming languages provide so much power it blinds people to thinking that they can solve big problems in other domains they don't have expertise in. And finally, if power is something that democracy distributes, right? It's something we try to transfer and balance and equalize. Should democracies distribute programming languages? This is President Obama doing an hour of code in DC. He announced the CS for All initiative this year, which is attempting to bring computing education to every public school in the United States. Is this something that we should be doing? Is sort of the obligation of democracies to distribute this power? This is an important question that we have to grapple with. Now, I spent the rest of middle school playing with code. Just a fair warning, I'm going to give you sort of an unflattering picture of me. Look at this terrible posture. This is me sitting in front of my computer at middle school, my brother looking over my shoulder to see what I'm doing. I spent middle school really using my coding skills to create. This was what my playground looked like. And I made things like this. I was interested in rendering 3D graphics and making text adventures and making games. I didn't make games to distribute them to the world. I just made games for myself and for other people like my friends to play. It was a very small world. And I used things like Quick Basic to do it. I also still used my calculator. The language in all of these cases, it was not the subject of interest for me. This was not why I was doing this. I was not intrinsically interested in anything about languages. For me, programming languages was media. It was a way for me to express myself, a way for me to show my ideas and share them with friends and sort of give a vision of the world that I had. It was a medium for expression. And this has a bunch of implications as well. If programming languages are media, and Marshall McLuhan teaches us that the medium is the message, what messages does programming languages entail? How do programming languages shape and bias and warp the kinds of programs we create? How do we reason about some of these biases in the expression? There are other implications as well. If programming languages are media, and media facilitates expression, how does PL facilitate expression? This is a photo of Mitch Resnick, who I mentioned earlier. He created Scratch. Alan Kay also had similar perspectives here around his personal dynamic media back in '76. Both of these men spent decades trying to understand how programming languages could foster creativity, but also how it limits it, and how language design can actually shape and constrain what it is people can say, what it is people can and can't create. So I took that perspective of media into my high school. This is Wesleyan High School in Oregon in the United States. PL was power and it was media for me, and in high school it transformed again into something else. Here's a photograph of my computer lab in high school. I signed up for this zero-period computer science class. It started before the rest of school at 7 a.m. That's how passionate I was about computing at the time. There were 8 of us in the class. About 7 of them came just to play multi-user dungeons and not really do anything in the class. And the class was kind of taught by this interesting character. He was a student from the local community college, and his teaching approach was to bring in his homework, challenge us to solve it, submit it in his class in the community college, and find out what was right, and then tell us who got the right answer in class. So I'm not quite sure what his incentive was. Maybe it was getting a good grade in his classes. But we were using Pascal in the class because that's what our PCs had installed. And at the time, my passion here, because of all of that media I'd been creating in middle school, was this club that I'd created with my friends. We called it the Computer Art Club. My friends were artists and musicians and other weirdos who like to do strange things with computers. And at the time, because I was obsessed with 3D rendering and all of the geometry behind rendering, I'd read about this game that was trying to render scenes with ellipses instead of polygons to create more organic shapes. And I was curious if I could do the same. And so my teacher had asked what I was up to. He saw some things being rendered on the screen, and I explained about these ellipses, and they were just rendering too slowly on these old machines to do anything interactive. So he suggested that I profile it and taught me how to use profilers. And we found out that my algorithm was spending about 95% of its time on square roots in the standard Pascal square root library function. So he suggested that I talk to my math teacher to find out if she knew of any ways of computing square roots faster, that maybe I could use those instead of the built-in Pascal library. So that took me to my calculus teacher, Miss Hudson. Now, she was no regular teacher. She had a PhD in math from Texas. She didn't know any algorithms for doing this, but she did have a network. She connected me to her advisor, who had this fascinating book on the history of Greek methods for computation, published in the 1920s. And through interlibrary loan, the little book showed up, and she gave it to me, sort of bursting with excitement that she'd sort of gotten this connection for me. I dashed home to read this archaic, sort of 70-year-old book. Here's the actual book and the text that was relevant to me. Inside of it and on these pages was everything I needed to know. It was square roots, cube roots, nth roots, all manual algorithms for computing roots or approximating roots. But the notation in this 1920s book was far from Pascal. It was even far from the math I'd been taught. It was its own notation for computation. It had a little bit of math symbols, a little bit of natural language, some other invented symbols. So my job here really was to translate from this book the core computational ideas into Pascal. And I eventually translated the algorithm and sort of greatly accelerated my ellipse rendering. But in doing all of this, I realized that programming languages were not just media, and they weren't just power. They were also notation, just like musical notation, for example. They were notations in a way that notations express abstract ideas, like the concept of roots or the rules of Tetris. And this became my view of programming languages for high school. Now, this view of notation has many implications as well. Notations model reality, which begs the question, what cannot PL model? What are situations that programming languages just can't describe? Do we need a different type of logic to model, for example, this trading room floor and all of the social and visual dynamics that happen on it? If PL is notation and notations help share information, right? It's what we use in order to convey ideas to other people. Are there kinds of information that programming languages can't share? What does it mean for a programming language to be comprehensible to other people, since that's the point of sharing notations, is to help other people understand basic ideas? And if PL is notation, and notations must be learned, what makes a programming language learnable? There's nothing about syntax and semantics that are natural. These are all things that are artificially created to share information. So what about language design choices affect the learnability of some of these notations? So I took that perspective on languages as notations off to college. After 5 years of obsession with code and art, I found myself a computer science major, sort of inevitably. I was also a psychology major. Now, PL was power, it was media, it was notation. I was eager to find out what else programming languages might be. And the person who taught me was my undergraduate mentor, Margaret Burnett. I met Margaret after seeing a flyer for an undergraduate research assistant position in the hallway. She was offering to pay me almost as much as the summer job that I was considering. She made a good pitch for being a professor and sort of how professor jobs are the best possible jobs you could ever have. I was completely sold. Not only did she end up teaching me a lot about research and writing and programming languages, but she also was the one who taught my programming languages course. Now, she framed it really as a programming language parade. It was a tour through a dozen languages. We dissected the trade-offs of all of the different design choices that they make and the implications of those design choices. We wrote the same programs a dozen times over, trying to understand the design space of programming language design. And she helped me see that actually programming languages come from people. They are designed things. These 6 people, for example, right, all designed programming languages, and every single one of them had to go through a process of understanding trade-offs and flaws and principles and values and priorities, the kind of thing that all of us in this audience think about. So there's a whole process behind all of these, and a whole set of people behind these decisions, which means they're really designs like anything else. Now, designs have certain requirements. For example, if designs have trade-offs, what are the trade-offs that exist in programming language design? How do we model this trade-off space? Which qualities trade off with one another when we're designing languages? Are there parts of this design space that we have not explored that evoke different trade-offs than we've considered? And if programming languages are designs, and designs come from process, what is a good programming language design process? This is David Kelly teaching a class at the D School at Stanford. He teaches a process he thinks is a good process. When we teach our graduate students to design programming languages, what processes do we teach them? What is a good design process for arriving at a good language? Another idea is that if programming languages are designs, and designs require prototyping, how do we rapidly prototype programming languages? Is it enough to jot down a sketch of a program and its syntax, or do we have to actually be able to execute these provisional sketches of PL ideas? And if it were trivial to prototype a programming language, how would that transform our discoveries of new programming languages by being able to do it rapidly, much more so than we can now? And finally, if programming languages are designs, and design exploits aesthetics for utility, what are PL aesthetics? What is beauty? What is parsimony? What is brevity? What are these ways of reasoning about programming languages aesthetics that go beyond soundness and correctness? Are there ways of reasoning about these formally, perhaps? Now, my next stopping point was graduate school. My time at Oregon State with Margaret was a very deep introduction to both HCI and software engineering and programming languages. But my passions in design and human behavior were equally strong, so the HCI Institute at Carnegie Mellon was the natural place for me to get a PhD. It brought together my curiosity about design and expression and notation and power, and helped me find more ways of seeing programming languages. And I found them in many compelling ways from lots of people. I was advised by Brad Myers up here on the upper right. He'd been working on the foundations of user interface toolkits and how to use programming languages to construct user interfaces. I also spent time with the late Randy Pausch, who'd worked on Alice and ran these really incredibly fun courses called Building Virtual Worlds, shown on the left here. And Brad had encouraged me to study the programming that happened in this course, just to find interesting problems to solve in research from an HCI perspective. So I did, and while I watched people construct programs with Alice and these virtual interactive worlds, I expected to see a lot of expression, like the kind of media perspectives I saw before, but what I saw instead really was just a big, long series of usability breakdowns, just things that were not working about people's experience with this interface. Students would express what they wanted, they'd never get it quite right, and this would lead to hours and hours of unproductive tweaking and debugging. So from this HCI lens that I had, the students' lack of understanding of the semantics of the language and their inability to see those semantics actually execute, to really understand the programming language semantics, these were fundamental user interface problems. So here is where I adopted this perspective of programming languages as interfaces to machines, as user interfaces. Sort of an inevitable view because I was at an institute concerned with interfaces, but it was also because computers and programming languages in particular really are and were the primary interface to computers. It's how we operated them originally. And this view has several implications that lots of people have explored. For example, if interfaces have to be usable, there's this natural question of how do we make programming languages usable? Andy Stefik at University of Nevada, Las Vegas, has been doing some great work in this area. He's found, for example, that statically typed languages reduce debugging time, that transactional memory prevents synchronization bugs, a whole series of interesting studies that demonstrate that certain features of programming languages are more usable than others. I mean, he's embodied a lot of these discoveries into the design of a new programming language called Quorum. He calls it the first evidence-based programming language. It's also a very accessible language. It's even usable by blind users because he's tried to make it usable in that way. Now, if programming languages are interfaces and interfaces have to provide feedback to users so they understand the state of the machine, what feedback do programming languages have to provide? What makes a good error message? One of my PhD students did this great study a few years ago that found just by using personal pronouns like I and we in error messages, novices read error messages more closely. They end up understanding the semantics of a programming language better and therefore are more capable of actually comprehending the causes of some of these errors and repairing themselves independently. And finally, if PL are interfaces and interfaces convey what's possible through affordances, how can PL convey what's possible? Is Stack Overflow really the best illustration of all of the things you can do with a language, or a bunch of examples that you put on a programming language website? Why can't we provide richer, more robust articulations of what's possible with a programming language, but also what's not possible? So as I got to the end of my graduate studies, you might be wondering in this period of time, why haven't I talked about the formal, logical, mathematical view of PL that we all use in this room? That's because I actually didn't encounter it until I started coming to conferences like Splash, ICSE, and FSE. This is me at my first ICSE, 4 years into my PhD, after several years of publishing exclusively at HCI conferences. And I must say, the encounter of PL as math was a bit of a shock. I'd spent my whole life thinking of PL as interface, media, designs, notation, power. And here was a community, this community, that actually viewed programming languages as fairly formally logical things. PL as math. Now, I realize ICSE is not really the home of PL as math. That might be PLDI, POPL, a bit of Uppsala here. But back in 2006, a pretty large proportion of the work at ICSE was formal methods, really with only a tiny fraction of empirical work. And in most of these papers, programs weren't expressions, they were propositions. This was the computing culture that Papert talked about. And what I learned was that PL as math had many implications that most of us already know in this room. Math has correctness, and so we ask, what does PL correctness mean? Math can be proven correct, and so we ask, how do we prove programs correct? Math concerns identity, so we think a lot about equivalence in programming languages. This is the whole history of theory of computation, right? So this math one is very well explored in computer science. Now that takes me to my final stop, and this was where I went to join the faculty at the University of Washington Information School. All of these perspectives that I had come with were sort of a good preparation for the vast diversity of perspectives I would encounter starting as faculty at this highly interdisciplinary place. Nothing and no place has really stretched my epistemological stances more than being amongst the faculty that come from just 20 different academic disciplines. Nothing's made me question my values more, in fact. So I want to share with you just a brief list of some of the other perspectives I've encountered around programming languages amongst my colleagues. One is sort of obvious, which is programming languages are like natural languages. They're about exchange. This is why we use the word syntax and grammar and semantics. So we ask these questions about languages like ambiguity. Does programming languages have ambiguity? Do PLs shape how we think? This is the Sapir-Whorf hypothesis, right? Do they structure our thought? Do they shape our thought? We might think of programming languages as communication. We tell a computer what to do. That's a kind of communication. So What if PL is communication? Should PL model developer intent? Should it develop common ground? Should PL express its intent to developers in a dialogue? PL can also be thought of as glue. 4 years ago, I co-founded a startup called AnswerDash and spent 3 years as its CTO and its lead engineer. And as a developer, it was really hard to think of PL as anything more than just an interface between APIs and frameworks and libraries and platforms. Languages and all of their features were just not that useful for routine web applications, for which there was so much we could already reuse. It was all function calls. Even conditionals and other loops were embodied in function calls. In a very functional way. So perhaps programming languages are just glue. They're about connecting things together. And that forces us to ask, what makes a programming language a good adhesive? What materials do PL adhere to? How far can you take that metaphor and really start looking at new perspectives on what PL should be? Here's another view that I got from some of my philosopher friends. What if programming languages are legalese? In software engineering, programs are often agreements between parties about what an application must do, should do, must not do. If programs are contracts, then programming languages are legalese. It's the formal and technical language of these legal documents that convey promises. If this is the case, who should legally interpret code? Are programmers lawyers because they're writing legalese? What is the equivalent of a judge in this metaphor? Take some of the implications of this, and we might start finding interesting ethical implications for programming language design. Here's another view, programming languages as infrastructure. So we can view programs as conduits for information in society, funneling and filtering and distributing all of the data that ultimately has meaning for people. Now, if we build roads with concrete and nails, that's infrastructure. We build information systems with programming languages. So if programs do this transmission, then programming languages really are the information infrastructure of society. And that forces us to ask some important questions about PL as infrastructure. How do PL decay? Who should maintain programming languages? Are programming languages a public good? How many people are taking care of COBOL and Python? For all of the programs that are written in those languages. And if those people were to disappear, what would happen to all of the programs and other infrastructure that it's built on top of? So I'm going to end with one last perspective. I had a sabbatical this past year, and one of the things I thought it would be fun to do is teach a class to high school students. So I taught a class of 7 South Seattle high school students this past summer. Few of them had ever encountered code before, and virtually none of them had any interest in learning to code. They were in my web design class because many of them would rather take that than the ballroom dance class that was in their summer college prep curriculum. So I had 11 largely disinterested students trying to get through a college prep program. And I asked them early in the course, what is a programming language? What do they think it is? What are the stereotypes they have in their head? And one of them said, and everybody else agreed, programming languages are a way out of poverty. Now, these are kids that are not particularly wealthy, and it's clearly pretty far from the definitions that we've talked about so far. But in a way, this is sort of the most dominant view of programming languages in the world today. In her world, the student that responded, she's surrounded by Seattle software companies, by wealthy entrepreneurs in the news, by a constant sort of nonprofit advocacy of learning to code. They have teens that barely finished high school. They live in poverty themselves. This view of programming languages as a pathway from their circumstance is an entirely reasonable conception of what they are. And it has a lot of implications. Governments create paths out of poverty. That's something that democracies do. Should our governments create these paths? Should they subsidize the creation of ways out of poverty via computation and programming languages? The rise of MOOCs is not doing that. That's really only reaching the privileged. Coding boot camps are the same. I mentioned the CS for All program before that the White House announced. Britain's also done a ton in K-12 CS education. What responsibility do we have as a community to create these paths out of poverty as part of this conception? If PL is a path out of poverty and paths have to be equitable in that everybody can access them, how do we make programming languages more equitable? Should government be funding projects that try to make programming languages more accessible, more usable so that everybody can learn them? Should they be funding things to create programming language learning opportunities for everybody? And finally, if programming languages are a path, and paths can only fit so many people, who do we lead down this path? In today's world, we don't really choose all that explicitly. We kind of let our culture determine who's interested, and we let our culture determine who we exclude and who self-excludes themselves. How would we choose explicitly? Do we look at innate aptitude? Do we believe that everybody can learn a programming language? And by what principles would we selectively encourage people to become interested in programming? Do we think everybody can be on this path because everybody's going to be doing some kind of programming in the future? After all, hundreds of millions of people write spreadsheet formulas. That's a kind of programming. And so when you step back and we look at all of these different conceptions of what programming languages are, these aren't even all of them. Across the past 17 years or so of research that I've done, it's really clear to me now that all of these views of programming language have research value, if not more value. They were productive in my personal life. They helped me move from one conception to the next, but they were also productive in my research. And yet the other thing that became clear about all of them is they all also are not only valuable, but they also have values themselves. Each one prioritizes really different human values. Math prioritizes certainty. Interface prioritizes efficiency. Design is about utility. Notation is about sharing. Media is about expression. Power is about agency, having freedom and independence. Language is about exchange, communication, understanding, glue, connection. Legalese is about promises. Infrastructure is about fellowship. And paths are about equity. And so you have to ask, with all of these values from all of these different perspectives, what values are behind our research? So when I look at my impression of what we spend our time on, most of our discoveries are about certainty. That's the value that we really have in our communities in computer science. To an extent, we care about the efficiency that people have with software that they're using. But there's a lot of values here that we actually don't explore all that deeply. So let's take a look at this space of values. And we can see that some are really about computing. These are the ones on the left that we've really concentrated on. And some on the right are really about people. We've spent most of our time on the left side. So there's this really important question of how do we investigate all of these values on the right? I want to go ahead and give 3 examples from my own work to try to illustrate how to investigate these and what some of the benefits are of investigating them. I'm going to start with one of my earlier attempts from my dissertation work to look at communication, programming languages as something that you interact with and tell computers what to do with. And I started with the idea that programming languages are how we do that telling, but also once we tell computers what to do with programming languages, they often don't do what we want, so we inquire why they did what they did. So that led to this research question: how do we interrogate program behavior? And that led to this first discovery of the why line for Alice. The idea here was to allow people to ask why questions about program output. So the program does something, it exhibited some failure, you should be able to ask the program why it did that. And using the programming language's semantics, give explanations in terms of the underlying causality of program execution. And this led to a pretty dramatic acceleration in debugging times, making people about 8 times as fast for the same bugs that they were trying to fix. That led to the Y line for Java several years later, which I used to show that we could scale this to large Java programs. This accelerated professional expert developers debugging. And several years later, I had a PhD student, Brian Berg, who just graduated. He looked at time travel debugging and reverse engineering in 2 systems called Timelapse and Scry. And these were explorations in trying to help somebody understand how a web interpreter was executing programs. Very similar ideas to the Y line. Now, Brian recently joined Apple and has begun upstreaming a lot of this work to WebKit, and that brings us back to these values, because what we have in WebKit is really this embodied value of helping people understand machines and helping machines understand what people want from them. This is creating all kinds of opportunities to help build tools on top of WebKit that really exploit this value. Now, the second example I want to look at is the perspective of programming languages as notation. I'm arguing here that notation is really about helping facilitate exchange, because we write things down in order to share knowledge with each other. And so the question that I looked at here in my work is, how do we make programs more readable? Readable, and not only readable, but comprehensible. So one of the first projects I did here was looking at how do we render code as rich text. This was about 10 years ago in a system called Barista. The idea here was to separate the idea of a program's text from the way that it's presented. You can present it in a variety of ways. So this was a structured editor that allowed you to create alternative views of any AST in a program's rendering. Another related project around that time that I'd done with Michael Koblenz, who was an undergraduate at the time, but is now a PhD student at Carnegie Mellon, he looked at how to make cross-cutting concerns across larger programs more readable and visible by taking parts of programs and rendering all of them in one place. So again, this was about how to portray this and how to help create notations out of existing notations that were more comprehensible. And finally, zooming ahead a whole decade, I now have two PhD students, Greg Nelson and Benji Shea, who are looking at how to teach people to read programming language notations. The idea here is to really decompose a programming language into its operational semantics and try to train people to understand and predict the behavior of each of those execution rules. And we found in some of our preliminary work that we can teach a programming language in about 3 to 5 hours to a rank novice who's never seen a line of code before in their life. Now, all three of these contributions are going back to this value of exchange. To the extent that people can understand how a program works and what it means, they can understand both how to manipulate it with the machine, but also how to explain it to other people. The final example that I want to give is programming languages as power. And this is really looking at this value of agency. Agency in the sense that people feel empowered to control what machines do, but also control the parts of the world that computing is interacting with. All of this work was led by my former PhD student, Michael Lee, who's now faculty at the New Jersey Institute of Technology. And he asked this really interesting question. What effect does power, and in particular the relationship around power, between a novice and a compiler have on learning? His observation here was that things like compiler errors actually take a very authoritative framing of the relationship between a person and a computer. The compiler is the one in charge telling the learner what they've done wrong. And it creates this really frustrating and discouraging dynamic of constant failure, right? It's constantly invalid syntax, invalid statement, everything you're doing is wrong. And so he wondered if we could reframe that relationship and try something that was more encouraging. And this led to a game called Gidget back in 2012, which framed the compiler as a reliable but unintelligent collaborator, placing the learner in the role as the creative problem solver. And this is actually a very authentic representation of what programmers do, right? You're using this tool that does what you say, but it doesn't know what it's trying to do or what you're trying to accomplish. You're the one with all the intelligence telling it what to do. And what we found is just through this reframing, just by trying to change the power relationship between a learner and a compiler, led to faster learning, but also more engagement. People would actually voluntarily learn in this game for longer periods of time because they trusted that they had a contribution to make to this collaboration. So this led to a series of studies that showed that very, very subtle design choices about error messages and data representation and how you assess knowledge in a learning game like this can have really powerful effects on learning and engagement. Mike eventually deployed the game back in 2015. Last year, it's already reached 10,000 learners, ages 8 to 80, and all of the design principles embedded in that were picked up by Code.org, which is a non-profit policy group that's trying to increase access to computing education, and they've reached, through those principles, tens of millions of learners. And again, all of that ties back to this value of agency. Now these 10 million learners have a deeper kind of agency with computing and machines. So all of these kinds of contributions change this distribution of what we know, and they change the values that we're disseminating into the world through research. And these values, because they're different, are really engaging new people in computing, and computer science research. And this is in turn sort of changing the values in our research community. But we should ask a couple of important questions about this distribution of values that we focus on. One is, what should the distribution be? Right? What's the right set of things that we want to focus on? Who should be doing the research? Is it all computer science research, or is it communication, psychology, sociology, other fields that should be looking at some of these values? And is any of this research going to happen if computer science doesn't explicitly embrace some of these values and encourage this work to happen? Maybe it's the case that these other disciplines don't know to ask these questions because we haven't asked them. Here's a couple of things that I think are true. I think that as a discipline, computer science doesn't have to explore all of these views, but it does have to encourage the exploration of these views. It does have to advocate for them to be explored. And maybe that's done in collaboration with other disciplines. And finally, to really equitably engage everybody in computer science does have to embrace all of these views, even if it's not going to explore them deeply. It has to show everybody that's learning computing that the values they bring to computer science are values that are embraced by the community, that CS is really more than just logic, because that's not a value that everybody's going to start with when they come to computing. So how do we do this? How do we accomplish some of these things? I've got a couple of concrete recommendations for what we can do. One, when you are choosing a new research question, consider a new view of programming languages. Start choosing research questions that look at new views. Maybe there are views that draw upon expertise and skills that you have that are close to PL as math, but maybe one step away from it. And when you're writing a paper, try to be explicit about your views of programming languages. What epistemology or what definition or what metaphor are you using? Perhaps you're using multiple distinct ideas of what programming languages are. And then close the loop on that. When you're reviewing somebody else's paper, try to evaluate it against the paper's view of programming languages and not yours. Don't judge something as not science because it's not the epistemology that you use. Recognize that all of these demand different methods and different theories and different techniques. And then finally, when you're teaching programming languages, try to be pluralistic in your claims about what they are. Try to explain multiple views on programming languages. My colleague Sriram Krishnamurthy at Brown does a great job of this in his programming language classes, trying to encourage everybody to come up with some understanding that is pluralistic about what the nature of programming languages are. And I think that if we do these things, we'll not only approach this inclusive computing culture that Papert wrote about, but we'll also create a more inclusive world in general, in which everybody's perspectives, everybody's values in computation are reflected not only in our work, but also in our society. Thank you.